jump very high and you block me. Do you know how high you can jump?
I don't know, because I never test out my jump.
So, do you want to test your vertical jump?
Yeah, sure. Let's go.
Okay, where do you want to jump? Paper?
Maybe take it long.
In this assignment, the vertical jump was chosen as a specific example to complete the three learning outcomes of this course. To get to LO1, problem of oscillatory rigid bodies in a two-dimensional plane should be resolved. To obtain LO2, a free body diagram and a kinetic diagram both to analyze the force acting on the body as well as in move. To prove LO1 and LO2, the time taken for an oscillatory motion at a standing jump was determined. Projectile motion is the motion of an object thrown or projected into the air. The most important statement is that the motion along perpendicular x, which is horizontal and vertical motion, are independent and so can be determined separately. Assume that the upward direction is defined as the positive direction and the acceleration in the y component is 9.81 meters squared, in x component 0 meters squared because gravity is vertical. Both accelerations are constant, thus the kinematic equation can be used. Kinematic equations are shown below. The figure also shows the plane of flight of a vertical jump. Based on the principle of conservation of energy, if all the force acting on the particles of the system are conservative, the formula below can be used when Ke represents kinetic energy and Ge represents gravitational potential energy. Next, based on the conservation of linear momentum for a system of particles, when the sum of external impulse acting on a system of particles is zero, we have a conservation of linear momentum. For impulse or force, it is the product of average force and time that come from the Newton's second law. Other than that, vibration is the oscillating motion of a body or system of related bodies displaced from an equilibrium position. Elastic force is produced when the spring is being stretched and compressed by the external force. The elastic force acts in the opposite direction as the external force. It tries to bring the deformed end of the spring to the original equilibrium position. It is according to Hooke's law. If the handling mass is displaced from the equilibrium position and released, then the simple harmonic motion will occur. The equation for the natural frequency of the oscillating system is like this. The natural frequency of the oscillator can be changed by changing either the spring constant or the oscillating mass. The stiffer the spring, the higher the natural frequency of the oscillating system. The greater the mass, the lower the natural frequency. Besides, the other characteristic of the oscillation system are the period and the frequency. The period of the oscillation is the time is taken an object to complete the oscillation. Frequency is the number of oscillations per 1 second.
The objective of this experiment: number 1, to demonstrate dynamic learning outcomes using real-life activities, which is the vertical jump in this experiment. Number 2, to solve dynamic problems of accelerating athletes doing the vertical jump. Number 3, to solve problems of accelerating rigid bodies in 2D. And lastly, to analyze kinematics and kinetics problems in vibrating particles. Moving on to the methodology. The experiment was conducted at Arena University of Malaya. The materials and apparatus used in this experiment are the vertex, measuring tape, sellotape, meter ruler, and marker pen. In this experiment, we assume that the motion of the jumping athlete is in projectile motion. Therefore, the free fall acceleration G is constant along the path and air resistance is neglected. Generally, the procedure starts with the vertex set up in an open space. Then, the position of standing vertical jump under the vertex is labeled with sellotape. Two basketball athletes, jumper A and jumper B with different heights, were to do the vertical standing jumps, and they reached the vanes of the vertex to measure the vertical height of their jumps. The number of the vanes reached is counted and recorded in the table. Each jumper is required to attempt the jump 3 times to get average values of the numbers of the vanes reached. The distance is then extended to 3 meters away from the vertex to conduct a running jump experiment. Both values, jumping height and jumping length, are calculated via Google Sheet. Dynamic problems of accelerating athletes doing the vertical jump, the problems of accelerating rigid bodies in 2D, and the kinematics and kinetics problems in vibrating particles in this experiment can be analyzed. So here we have our manipulated variable, Darren Lee as the jumper A, Megat Ayman as the jumper B, both age the same and weight the same but different in heights. Darren goes to gym regularly about 4 times a week, but Megat Ayman plays basketball regularly. So let's take a look at our responding variable. Jumping height is the displacement in y direction. Jumping distance is the displacement in x direction. There are standing vertical leap and 3-meter running vertical leap. 2 types of jump attempted by both jumpers. The average jumping distance and the average jumping height is recorded in the table. Before we start the calculation, we have to take note some of the constants. As for the standing reach, Darren is 220 cm, Megat is 207 cm. The gap between 2 vanes is 1.25 cm. The gap between the first vane and the base is 0.55 cm. The vertex base height is 243.84 cm. In order to calculate the jumping distance, we use the pixel coordination to locate the position of the foot before jumping and after landing. For all of the attempts, we find the average displacement, and then we convert the pixel unit to SI unit. To calculate the jumping height, we use the formula of the total number of vanes reached plus the base height of the vertex minus standing reach of the jumper. For all of the attempts, we get the average number of the vanes reached, and then we calculate the total height reached. Eventually, we will get the vertical distance traveled, which is the jumping height.
Hello, my name is Yuan and my metric number is S2116568. Now I'm going to talk about the calculation and discussion for learning objective 1, which is to solve dynamic problems and accelerating particles. In the experiment, we measured the vertical and horizontal displacement for jumper A and jumper B, and then we found out that jumper A has the average vertical displacement of 0.718 meters and average horizontal displacement of 0.6296 meters, while jumper B has the average vertical displacement of 0.6406 meters and average horizontal displacement of 0.6138 meters. After that, we used the data collected from the experiment to find the velocity and acceleration in x and y directions for both jumper A and B. In this calculation, we assume that there's no air friction or other forces acting on the jumpers, so the horizontal acceleration is assumed to be 0, and the vertical acceleration is equals to negative 9.81 meters per second square when t is greater than 0. With the formula listed in here, we found that the initial vertical velocity Uy is equals to 3.7556 meters per second, and the velocity before the jumper air reached the floor is Vy equals to negative 3.7548 meters per second. After that, we also find that the initial horizontal velocity Ux is equals to 0.8224 meters per second. Finally, we also found the final horizontal velocity Bx equals to 0.8224 meters per second. Besides that, with the data collected from the experiment, we also further calculated other values such as the time taken to reach maximum height t half equals to 0.3828 seconds, and the total hand time t equals to 0.7656 seconds, and the initial value u equals to 3.8446 meters per second. The angle of initial velocity delta u equals to 77.65 degrees. The final velocity v equals to 3.8439 meters per second, and finally the angle of final velocity delta v equals to 77.64 degrees. After that, we also calculated the same values for jumper B, and we used the same formulas and assumptions that we use in jumper A. And we got that the initial vertical velocity Uy is equals to 3.5452 meters per second, Vy is equals to negative 3.5455 meters per second, Ux is equals to 0.8492 meters per second, Vx is equals to 0.8492 meters per second. For the other findings for jumper B, we found that t half is equals to 0.3614 seconds, t is equals to 0.7228 seconds, u is equals to 3.6455 meters per second, delta u is equals to 76.53 degrees, v is equals to 3.6458 meters per second, and delta v is equals to 76.53 degrees. After all the calculations, let's compare and discuss about all the results between jumper A and B. First, let's compare the initial and final vertical and horizontal velocities of jumper A and B. From the result, we can see that jumper A has higher initial and final vertical velocity, but lower initial and final horizontal velocity than jumper B. This may suggest that jumper A can jump higher due to higher initial and final vertical velocities, and jumper A's jump is more efficient than jumper B because jumper A wastes less energy in the horizontal velocity. Next, let's compare the hang time of two jumpers, and then we can see that jumper A has longer hang time, which means that jumper A can stay in the air longer than jumper B. Lastly, let's compare the angle of velocity of two jumpers. According to the research report by Christensen at 2020, he stated that the peak knee flexion angle of the jumper has a significant impact on the jumper's maximum jump height, and he suggested that the optimum peak knee flexion angle is between 87 to 107 degrees. And from the result, we can see that jumper A's angle of velocity is closer to the suggested angle, so jumper A can jump higher, and jumper A's jump is more efficient than jumper B.
Let's proceed to L2, which is a solved problem of accelerating 2D bodies. First, we analyze the force and acceleration acts on the jumper before he jumps and when he reaches the peak. There are a few assumptions made, like there is no frictional force and air resistance, as well as the jumper acts as a vertical force of 2,141 Newton towards the ground. Based on the free body diagram drawn, you can see that there are three forces acting on the jumper before he jumps, which is the split, his muscular tendon force towards the ground vertically, and the normal force acting on his foot. There is no acceleration yet in the kinetic diagram as he is not moving. Throughout the calculation, we found out that the normal force acted on each of his foot is equal to 1,364.8 Newton. This is related to Newton's third law of motion, which states that to every action, there is an equal and opposite reaction. Hence, when the jumper pushes an amount of force towards the ground, an exactly same amount of reaction force is being applied onto the jumper and sends him into the air. Moving on to the second free body diagram, there's only a downward force, which is his weight, acts on his body, while the kinetic diagram shows an upward acceleration as an assumption. Throughout the calculation, we determine that the acceleration is equal to negative 9.81 ms negative 2, which indicates that its direction is opposite to the assumption. This can be explained by the Newton's second law of motion, which states that a particle experiences an acceleration in the same direction as the non-zero net force. Next, the conservation of energy is analyzed through three positions, which are during the jumper takes off the ground, when he reaches the peak, and when he's landing. Based on the calculation, from position 1 to position 2, the kinetic energy is totally converted into potential energy, while from position 2 to position 3, a 0.16 joule of energy is lost to the surroundings due to abrasion. In fact, there is actually elastic potential energy stored in the tendon before the jumper jumps. Similar to a compressed spring, when the force is being removed, the elastic potential energy is immediately converted into the kinetic energy and the body lifts into the air. The amount of energy stored can be computed via the formula on the right.
The tendon acts like a spring which stretches and compresses when the force generated by muscles is applied on it. Its stiffness plays an important role while a person is doing any kind of leg movements like walking, running, and especially jumping, which contributes to how high one can jump. A high tendon constant value indicates that the tendon is stiffer. Hence, there will only be a small change in length when the force is exerted on it. More force is needed to compress it so that more elastic potential energy is being stored and turned into kinetic energy soon after. Jumper B has an Achilles tendon stiffness of 287.8 kN per meter when its tendon is assumed to stretch for 5 mm. The tendon vibrates with a natural frequency of 69.258 radian per second and complete a cycle in 0.0907 seconds. Within a second, it accomplishes about 11 cycles. All these values are subjected to change once the tendon becomes stiffer. From the perspective of dynamics, vibration in tendon can be categorized as damp force vibration, as the motion is caused by external muscle force. Both internal and external frictional force exist between the muscles and cells will gradually stop the vibration waves. There are some other factors that affect jumping height. First, the effect of arm movement. The arm swing helps in jumping performance by increasing the takeoff velocity. This is because as the arms swing up, there's an opposite reaction of the body being forced downward, increasing the force pushing off the ground. Next, knee bend. Jumping is a process involving energy conversion. As the knee is bent, bones and muscles start storing elastic potential energy, and when taking off, the conversion takes place between potential to kinetic energy, which makes it easier to overcome gravity. Thus, the jumper can jump higher. Furthermore, types of shoe also affect jumping height. Extra cushioning in the heels can prevent the feet from getting injured from too much of force absorbed when taking off so that the jumper can jump higher. Jumping takes power. The less weight on jumper's feet, the more power he can put onto the ground, the higher he can jump. The more flexible the shoe is, the faster its momentum will be. Thus, if a shoe has more momentum, the jumper will be able to jump higher with it as compared to jumping with the less flexible shoes with less momentum. Lastly, running jump enables the jumper to maximize the vertical jump velocity at the point of takeoff while having sufficient horizontal velocity to carry his body moving forward.
In conclusion, the jumper A can jump higher than jumper B because jumper A has higher vertical velocity, and jumper A jump is more efficient than jumper B's jump because of lower horizontal velocity and better peak knee flexion angle. Besides that, the other factors that may affect the jumping heights of the jumper are the run-out momentum, the shoe type, and the arm movement of the jumper. In addition, the tendon stiffness, the natural frequency of tendon, torque of the tendon vibration, frequency of the vibrating tendon during jumping can affect the jumping height of the jumper as well. Finally, thank you very much for listening to our presentation today, and this is all from our group. Thank you.